Hello, my name is Patricio, and welcome to another episode of Machine Learning. Today we'll talk about binning, what it is, and what is an important subject in the realm of machine learning. Let us start with the basics. Binning in itself is not yet building the model, but it's a type of data transformation sometimes loosely called discretization. Binning is essentially the process of transforming numerical continuous variables into a small number of categorical classes, which we call bins. Like this continuous straw, which we divide into separate categories for easier manipulation. For example, having very large, medium and small bins instead of just one continuous number. Like any initial data handling exercise, it is a must to inspect and explore our data first. Binning allows for a better understanding of the distribution and its relationship with the variables we're trying to predict. It makes it easier to visualize, and some models and algorithms prefer dealing with categorical variables and continuous variables as long as you keep the number of levels low. Binning may improve the accuracy of the predicted models by reducing the noise of nonlinearity. And finally, binning allows for easy identification of outliers, invalid and missing values in any numerical variable. There are two major types of binning, supervised and unsupervised. And the difference between the two is in the supervision of the binning.
Really, nigga?
Not really. The difference between the two is that in unsupervised, the binning criteria doesn't depend on the variable you're trying to predict, and all the bins follow the same pattern. Supervised binning takes into account the y variable that you're trying to predict and to optimize the binning process, defining the bins depending on their explanatory power. The most common way of doing this is through entropy-based binning algorithms. Here, when we say entropy, we mean the expected information or information content that the bins reveal. Say what? Okay, or in easier words, how much each bin is able to explain of the variable we're trying to predict. This is a key process to improve your machine learning models, because at the end of the day, by using supervised binning, you make everyone's life much easier. Yay! But how will we apply this? As in any supervised entropy measure, the lower the entropy value, the better. Entropy-based method uses a split approach. Intuitively, it finds the best split so that the bins are as pure as possible.
They see me rolling.
Formally, is characterized by finding the split with the maximal information gain, also known as entropy gain. At a broad level, this is what the algorithm does with entropy-based binning. 1. It calculates the entropy for your data. And 2, for each potential split in your data, it calculates entropy in each potential bin, calculates the entropy gain, and finally selects the split with the highest entropy gain possible. Recursively, perform the partition on each split until the bins are as optimal as possible, giving a certain threshold. Okay, this might seem like a lot to tackle at the beginning, but luckily there are many tools that do all the dirty work for us, that's right. And there are plenty of R and Python libraries that perform it pretty well. Let us show you with a little example how to run the supervised binning using R. Woo! Using the SM binning package, we go through the basic steps in R. Using the embedded Chilean credit data, we tweak the code here and there, and voila! Woohoo! The bins are done. So easy, so beautiful, so simple. Look at those bins. There's so much entropy gain, so beautiful. I think I'm gonna cry.
Gotcha, bitch.
So that's it for supervised binning. You can check the code and other tools used and examples down below. And thank you for joining us in another episode of Machine Learning. Hasta la vista.